All right, let's kick this off. Thank you all for coming today. It's really great to see so many people. First of all, quick introduction. My name is Connor. I am the Deputy Director and Head of Operations for Adept Canberra. So I became involved in Adept a couple of years ago now, early on in the starting of Adept Canberra. I've had a bit of experience running an Adept project with our disaster response robotics project, which you'll be glad to know did involve a microcontroller. This is going to be the first in a series of upskilling sessions that we're going to be running. For each week, we've chosen a key technology that we think could be useful to you, either in a personal or Adept project or out in the industry. Today, I'll be talking about microcontrollers and single board computers. Some of you are probably wondering what those words mean or if there's even a difference between them. And actually, to get an idea of that, I'm going to do a quick poll, which should go live now. And I want to get an idea of what you guys know. To give me a bit of a baseline. So I'll give it a minute or two. Okay, it's quite an even spread. 37% have used them only as part of a university course. 32% have used them outside of university, perhaps in an Adept project. 20% have heard of them, haven't used either, and 10% have absolutely no clue what I'm talking about. Okay, the numbers are equally balancing a bit. So part of the reason we decided to run these sessions is to provide you with enough of an introduction to the topic that you would feel confident understanding the basics and actually using the technology in a project. I've had a bit of experience with microcontrollers and SBCs, as I'm sure you're glad to hear. And one of the things I've often struggled with is the excessive jargon and technical terminology around topics like this. Like, what is the difference between a microprocessor, a microcontroller, a system on a chip, a single board computer? And that's going to be a big part of what I'm going to try to answer today. And at any time, if you've got a question, you're like, Connor, that's unclear, you just made that up, please feel free to raise a hand, send a question to the chat, whatever you need. To kick it off, what's included today? So we'll go through a bit of a definition of each of these topics I'm going to be talking about, the core system architecture behind each of them, a bit of history, use cases, including prior Adept projects that we've used them in, applicable sectors, so where you could find a job with a bit of knowledge behind a microcontroller or SBC, important design considerations, common pitfalls, and some point of contact and useful resources. Quick disclaimer, it's just a bit of an introduction. So as always, make sure you do your due diligence. Probably doesn't have the same safety concerns as some of the other presentations we might be giving. One of them will be on drones, but as always, do your research, be safe. What the hell is a microprocessor? So a microprocessor is a central processing unit, a CPU. And that's essentially a device that executes set instructions from a piece of memory. This will be the core of any microcontroller or single board computer. And generally, you'll need additional hardware, such as memory to store the code, input-output devices to actually do something useful with a microprocessor, and often things like a graphics processor to handle displaying anything to a screen, or potentially a radio chip to communicate with other devices via Wi-Fi or Bluetooth. You won't generally use a microprocessor by itself, certainly not in a student project, and even in the industry, except for in specialty cases, you don't tend to see them used by themselves very often. Which brings me to the microcontroller, which is a small electronic device that contains a microprocessor as well as several other devices. Generally, you might have encountered an Arduino. The Arduino Nano is the one pictured in the bottom right there, which is a fairly common low-cost device, microcontroller device, and it contains a microprocessor as well as circuitry to do a bit of flash circuitry. So that's a memory to store the actual the code that needs to be executed. It contains the input-output pins that you can see along the bottom there, and it contains a connectivity device, in this case, the USB circuit, which allows you to program it just via your computer. Generally, a microcontroller is low cost and low power, and it's usually programmed with a embedded programming language such as C or MicroPython, and I'll get to the difference and how that compares to a normal programming language later. But generally, there is not an operating system such as Linux or Windows running on a microcontroller. There's always exceptions to these rules. You technically could run an operating system on these. I've seen it done, but it's usually a conscious choice not to. And some of these things the definitions can be a little bit blurry at times. So I hope I'll give you enough of an idea to be able to make a decent call most of the time. In the top right there, I've also got a Raspberry Pi Pico, which is a microcontroller, and it is different to a normal Raspberry Pi, which is actually a single board computer. And I include that as a bit of an example there. A system on chip is an integrated circuit that contains a microprocessor and one or more co-processors. A system on chip can contain any number of components, including storage, memory, a graphics processor, and potentially radio chips. Essentially, it's a microprocessor or a microcontroller, but with a lot of additional components. And this is one of those cases where it sort of does blur in a little bit with a microcontroller, but one of the key things is that it does contain all of the things on the same chip. It forms the core of a single board computer in much the same way that a microprocessor forms the core of a microcontroller. Mm-hmm. There's a lot going on there, but I think it'll become clear as I explain what a single board computer is. So all of you would have used a desktop computer, a personal computer, or a laptop. A single board computer is the same fundamentally. You're looking at the same core components, including a CPU. In this case, it's implemented through a system on a chip, an SoC, but it's no different really to the Ryzen or the Intel processor that might be in your computer they're using today. It's generally more powerful than a microcontroller, as I hinted at earlier, but it can be a little bit unclear. So an SBC contains additional input-output elements, including HDMI, Ethernet, USB. They don't exclusively have to have that. Some, for example, the Raspberry Pi there has Ethernet available, whereas other ones like the Raspberry Pi Zero only has HDMI and micro USB. An example of an SBC is the Raspberry Pi or the NVIDIA Jetson Nano, which is pictured in the top right there. Now, when you're working with an SBC, the good thing is that it's usually really easy to transfer the programming knowledge that you have from developing in Python on your computer or Java or C#, because you'll generally use the same languages. So a common general purpose languages that you might use do include Python, Java, C or C#, but really there's no limit. So anything you've encountered in your engineering or software engineering studies will usually be an applicable language for a single board computer. So microcontroller, how does it work? So as I hinted at earlier, the CPU executes instructions from memory. So when you program it from your computer, when you plug an Arduino in and you upload code, that gets stored on what's often referred to as flash memory. Flash just means that it's, in a way, you could almost visualize it like taking a photograph. It stores that data and it saves it in non-volatile memory, which just means that it will be persistent when you unplug the device and plug it in, so you don't have to flash it each time. The code can be re-flashed or reprogrammed unlimited times from a computer, and generally the code you write will be designed to interact with the GPIO pins on the board. So if you look at the diagram on the right there, the digital pins and the analog pins, which are along the top and the bottom there, those are the main input-output elements of a microcontroller. The example I have here is an Arduino Uno, which is just a popular microcontroller board, but the same will apply for pretty much any microcontroller. The awesome thing about these is they can interface with almost anything. So if you go online right now and you decide, hey, I really want something that can detect when I put my hand near it, or the temperature of the atmosphere, or atmospheric pressure, any sort of sensor, you can generally plug it straight into one of these pins here and you can read data off it. In theory, you could interface these with other microcontrollers or other devices, and that's a pretty common use case that I'll cover later. And one of the key advantages of microcontrollers is that they often have analog inputs and outputs as well. So in the bottom right there are 5 analog pins, and I will point this out just because single board computers rarely have analog circuitry in them. So it is a unique benefit that I will go a little bit further into later. Also important on the board there is the actual microcontroller, which is the large integrated circuit chip right in the center there, labeled as an Atmega 328 microcontroller. And one of the really interesting things about microcontrollers is that you can actually use that chip there as an independent device. So you can actually remove it from the Arduino, plug it into a breadboard or onto a PCB board and use it directly. It does take a lot more circuitry. You need, for example, you might need like a voltage regulator and some other additional circuitry to actually get it working, but you can actually use them independently, and it can be a really good choice for projects that require a small scale, a small footprint. Single board computer, it does look quite similar. One of the key things you'll probably notice immediately is the additional ports. In this case, you've got a HDMI port, USB ports, and an Ethernet port. These are usually found on a single board computer, and you'll notice that they're similar to the ones you'll find on a desktop or a laptop computer. An SBC will usually also have a micro SD card or a solid state drive for storage. The average micro SD card hold 32 gigabytes, 64 gigabytes, something like that, and a solid state drive would be even more. If you compare this to an Arduino, which might have, off the top of my head, a few hundred kilobytes, so we're talking several orders of magnitude less for an Arduino or a microcontroller, whereas a single board computer can have really unlimited storage. And people do use these for mass storage purposes. So it's a pretty popular application to use a Raspberry Pi for storing movies, movies and music and TV shows, for example, on a home server. So that would require external drives, but they can all be attached through a USB board. Now, one of the differentiating factors of a SBC is that it will usually run an operating system. And I sometimes use this as the main distinguishing factor between a single board computer and a microcontroller. But as always, you could run an operating system on a microcontroller if you were brave enough. And so what this means is when you operate with an SBC, whenever you write code that's supposed to run on it, you'll usually upload it or download it onto the micro SD card via the internet or a USB flash drive or something like that. So there's no flashing process in the same way that a microcontroller works. And once you're actually using the SBC, you'll execute it in much the same way you would run a program on your laptop. And so much like a microcontroller, you will have access to GPIO pins. At the top there of the diagram, you can see the 40-pin GPIO headers, and these serve a similar purpose to the Arduino ones. You can do the same sort of interfacing with sensors, with motors, servos, a lot of additional external hardware. The capabilities are quite similar. And this is one of the things that's worth considering when deciding is what sort of devices you want to connect, whether they're via GPIO pins or USB and Ethernet. And I will cover that properly and decision-making between the two shortly. Bit of history behind microcontrollers. So it was 1971 when Intel introduced the first microprocessor, which was the Intel 4004. It was designed for use in calculators. One of the most interesting things about computer history and microcontroller history is Moore's law, and you might have heard it either directly in this context or in some other abstract, unrelated way. It's often used to describe other areas of technological advancement, but it does have its origin here in microchips and microcontrollers. It states that the number of transistors in each microchip doubles roughly every 2 years. And over here, we've got a graph of the first, 33 years of microcontroller development, and it does follow quite closely. It's completely revolutionized everything we've done. I don't think that needs to be said. You're all currently using various microcontrollers and microprocessor hardware just to view this Zoom call. Use cases. So below I've provided a few key use cases for both microcontrollers and single board computers. The microcontroller ones, so the first I've provided here, and just quickly, this slideshow will be available to everyone afterwards. It should be on the Adept community Slack. But microcontrollers, a servo motor controller is a really popular application. So potentially you can use them for almost all basic robotics projects. Interfacing them with servos, with motors is usually really straightforward. Anyone who's done engineering ANU would have done it even in the first year courses with the Rover project. And I'm sure Adelaide Uni's done something similar. The Adept stringless guitar might use a microcontroller to read the data from the laser distance sensors, take that data and then send it via USB to a single board computer or a laptop or something as a input to a digital audio software. The Adept drone project uses them for the flight controller on the actual UAV drone, the unmanned aerial vehicle drone. And that's a really interesting one because it is a situation where you could use a single board computer. And I'll cover that a little bit further in a minute. For examples of a single board computer, we have a link there to a few NVIDIA Jetson computer vision projects. And this is a really big application area that I think is a really exciting thing. And we will be going a bit further into depth in a follow-on upskilling session on machine learning and AI. But it's really interesting what you can do these days with a small ML AI enabled SBC board. A link to machine learning using a Raspberry Pi, and robotics, of course, the Adept disaster response robotics project, which I've led for the last year and a bit. The fantastic news is if you become good with microcontrollers and single board computers, you can find a job anywhere. So they have a huge potential application in space technologies, robotics, mining, and embedded systems. But honestly, if you can name an industry, an engineering industry, there is a spot for a microcontroller or a single board computer. Here I've got a brief comparison of some of the most important factors to the differences between single board computers and microcontrollers. Processing power will be, of course, a considerable part of the decision-making process. So what do you want to do? What do you want to achieve? A single board computer is suitable for most applications, especially high throughput ones. So anything involving large amounts of data, if you're reading camera data or stock market data, anything like that, you want to be able to process a lot of information, and that will require processing power and also memory or RAM. A microcontroller, on the other hand, is better suited for doing one or two small, low-level tasks predictably and reliably. And this is one of the key advantages of microcontrollers, and the fact that they don't run an operating system can be quite beneficial. When you use a single board computer with an operating system, you have to deal with things like packages, so software updates, vulnerabilities, the security considerations of having a internet-enabled or external-facing device. And so having a microcontroller can actually be a really good idea if you just want something simple that does one or two things reliably and predictably. The cost is another factor. Microcontrollers are generally dirt cheap. I've said between $5 and $50 there, can vary. Single board computers, anywhere from $20 to $200 to really could be $2,000. Really depends how much you're being funded and what your application is. Networking and connectivity is, of course, a major consideration. So one of the most interesting things that's happened since I first started working with microcontrollers is the advent of Wi-Fi and Bluetooth enabled microcontrollers. It wasn't a thing 10 years ago, even 5 years ago. It was only just becoming available for affordable prices, but it's certainly been another factor that sort of blurred the line a bit. I provided a few other applications there for each, and one of the things under microcontrollers there is low power applications, which does tie in with basic smart home devices and things where you actually just need occasional events to happen. So for example, light switches, any sort of smart home light switches will use microcontrollers because you need it to be low power. It just does a single event, a single, what's a good word for it? A single thing predictably and reliably. For a single board computer, I've also put smart home devices on that list, although in this case, I'd look at things more like a voice controlled speaker or a smart display. If any of you own the Google Home or the Amazon Alexa devices, those will all use a single board computer within them. So if you've chosen to use an SBC, the next decision will, of course, be which SBC. And you might have heard of a few of them, such as the Raspberry Pi, and I have mentioned the NVIDIA Jetson. How do you make that decision? And those are only two of the options. What about the others? And I want to give you a bit of an idea now of how I would go through such a thing. The three key things I've put here are size, capability, and connectivity. It's not the only factors to look at, but I think they cover the broad spectrum of available devices. A Raspberry Pi is the most common one, and you might even have a couple of them. You might have used them as part of a university project, and it is a fantastic starting point. If you need something smaller, there are options such as the Raspberry Pi Zero, which omits several ports to save space and is, as a result, about the size of half a credit card. It's extremely small and it still has respectable performance. If you're looking to do anything with machine learning or artificial intelligence, the NVIDIA Jetson is a fantastic choice. And I just give these as examples. It's no specific recommendation or endorsement, but these are ones I've used extensively. For connectivity, some boards like the NVIDIA Jetson actually contain additional ports, such as a M.2 slot, which allows you to plug in a high-speed solid-state drive or a Wi-Fi card. This has actually been an interesting one for me personally, because in high school, I did a robotics project where we actually needed to stream several camera feeds at the same time to a separate computer. And we very quickly ran into the limitations of a Raspberry Pi. It has a built-in Wi-Fi chip on the Raspberry Pi that was sufficient for a single camera feed, but we couldn't reliably get 2 or 3 or 4 camera feeds going at the same time. And that was actually when we decided to look into additional options. We toyed with buying a USB Wi-Fi dongle for the Raspberry Pi, and I think we saw a slight improvement, but we were actually reaching the bandwidth of the USB ports, the maximum amount of data that you could transfer through the USB port. So we actually looked into a NVIDIA Jetson, or a similar board at the time. And with the M.2 slot, we were able to add in a Wi-Fi card that could transmit, I'm going to say about twice the total bandwidth of the USB port. And this was huge for us because it wasn't something we'd known how to solve until we tried it. There wasn't a huge amount of documentation on it, but it's a important factor to consider, and one that I've actually had a bit of real world experience with. When choosing a microcontroller, you'll probably come into the same factors to consider. So size, the two photos I've provided there are of the Arduino Uno and a AT Tiny 85 respectively. These are two similar boards, two similar devices in terms of capability. The Arduino is slightly more powerful, many more input-output ports, but they are both, I believe, 8-bit processors and of similar sort of, workflow. So you can program them both with the Arduino IDE software, and they're sort of in the same technology family. But as you can see, they're very different in size. So size is a factor that's always going to be important, and there are options for larger devices such as the Arduino Mega, as well as smaller devices that might be integrated with other components. So for example, the Arduino Uno has an IoT version of itself, which is the same size, but it has additional Wi-Fi cards. Sorry. As for capability, this is going to be something that differs a lot between different microcontrollers. So on the cheap side of the spectrum, there are things such as the Arduino Nano, the Raspberry Pi Pico, or the AT Tiny 85 there. On the other side of the spectrum, you have things like a Teensy 4.0 or an ESP32. I'll cover the ESP and Teensy a little bit in a second, but they're a fantastic example because they integrate a lot of functionality that you potentially might need for a very specific purpose. And it's a little bit hard to give a recommendation, a broad recommendation, but they have a lot going for them in terms of availability of functionality in terms of libraries, hardware, and connectivity. So on the subject of connectivity, there has been a rise of these Internet of Things Wi-Fi and Bluetooth boards. They're really, really popular, and they've come down in price significantly over the last few years. The ESP32 is probably the most popular at the moment. It's a Wi-Fi and Bluetooth enabled microcontroller. You can get them for about $10, and they're not very expensive, and they are really well supported by a large community of developers, and they've been used for everything from basic computer vision applications to radio communications, and pretty much anything you can think of doing with a microcontroller. Arduino have a similar range of IoT-enabled devices. They are a bit more expensive, but they have similar capability. So now I want to run through a bit of an example. When I wanted to do a robotics project, one of the things we had to consider was, what do we need to do, what do we need to achieve with this robot, and how are we going to achieve that with the technology, and what technology will we require? So from the use case, so the leftmost node there, I've got the decision there between simpler, cheaper, or high capability and scalable. For what we wanted to do with robotics, we decided we wanted something that was high capability. We could have achieved some of what we wanted to do with a microcontroller. For example, servo control is something you can certainly do with a microcontroller, so we could have driven the robot with one of them. but we wanted to have the ability to do things like the video feeds, a web-based control interface, and potentially down the line, machine learning applications. So being able to recognize hazards and people with a computer vision enabled camera. From there, we actually originally decided for the Raspberry Pi, and that was the starting stone of our project. And to be honest, if you're looking at a single board computer, it's always a fantastic place to start. But we did realize after a while that we wanted to take advantage of some of the features of a Jetson Nano, such as the machine learning and AI capabilities, as well as the high-speed interface for Wi-Fi. So this tree is a really good starting point, I think, for most projects. On the microcontroller branch, I've got the three options there of an ESP32 for Wi-Fi integration or any sort of Bluetooth or Wi-Fi project, so anything Internet of Things or smart home. It's a fantastic choice. For something that's basic and low cost, an Arduino Nano or an Arduino Uno is a very well-supported, well-documented, and easy-to-use choice. And if you want something that actually has a lot of processing power, the Teensy 4.0 is fantastic. Common pitfalls. The first of which, I think microprocessors are often conflated and confused with microcontrollers, and you will find that they are sometimes used interchangeably, but microprocessors are rarely used on their own. They simply just lack the required capability to be useful without additional circuitry. How do you avoid choosing an SBC instead of a microcontroller or vice versa? Generally, basing it on something like this tree here, or understanding exactly what technology you need out of each of these devices is a really good step in the right direction. And how do I avoid choosing the wrong microcontroller or SBC? To be honest, I don't think you really can. Unless you specifically know your requirements outright. So if you know you're going to be doing a machine learning application, you might be better off going with an NVIDIA Jetson Nano. But in most cases, you can often make a good start with a Raspberry Pi or a Arduino, and then you can scale up when you need to. I've provided a few useful resources here, which will be available on the community Slack. One of my favorites is this website here, the first one, which is pinout.xyz. It is a really simple website. It just gives you a detailed look at every single one of the GPIO pins on a Raspberry Pi, what it is, what it can be used for, and its name for when you want to use it in software. It's a fantastic resource and one I use all the time. I've provided a few other tutorials here on doing basic input-output and operations with an Arduino, so turning an LED on, controlling a stepper motor, and receiving temperature inputs, as well as a quick guide to uploading to an Arduino that doesn't have a USB port, which is something I've had to deal with a few times, and will certainly be something you encounter if you end up doing much work with microcontrollers. A few of the past projects we've run include the Rubik's Cube solver, which used a Raspberry Pi. And this is actually a good example of a project that used computer vision on a Raspberry Pi. So it is absolutely something you can do. You certainly don't have to choose a NVIDIA Jetson or something like that. The ROIDS project, which was the Rapid Object Identification Data System, a very forced acronym and I love it, also used a Raspberry Pi. The Disaster Response Robotics project used the Jetson Nano, which, like a Raspberry Pi, is a single board computer, but it does have the ML and AI capabilities that come with having the dedicated graphics unit on it. The ARD rockets use a microcontroller for the parachute deployment, which is, I think, a really good example of the doing one thing reliably and predictably, because that's exactly where you want something that is reliable and predictable. At the bottom there, you can find my Adept email address. Any questions whatsoever, please feel free to reach out to either myself directly or the engineering or technology at adept.org.au. Those, I believe, are forwarded to key people who will be more than happy to answer your questions. I'll provide a few more resources in the appendix, but I believe that is all for now. Thank you all for listening to me rant about something that I am quite passionate about and not very good at talking about, but I really enjoy it. And it's fantastic to be able to share some of this knowledge with people. Part of the reason why I chose microcontrollers and single board computers was a conversation with a friend of mine. It was only a few months ago, I think, and it was a project that he thought up, and he wanted to do it with a Arduino. And I mentioned to him he'd probably be better off with a Raspberry Pi. And he was like, why? And I realized it's not intuitive. And it's not something that I think is taught in universities or anything like that. And I hope today has cleared that up a little bit, hopefully without too much of the crazy jargon and terminology that often sneaks its way into discussions about computer hardware. But if it did, apologies, but hopefully you have this deck available now, and hopefully you can refer to that whenever you're working on an Adept project or even in the industry. Thank you all for listening. Any questions, please fire away. I'll be sticking around for 10, 20 minutes, however long. And if you've got any questions, I'd be very happy to answer them.
I think I've got a question, Connor. So, you know, for those of us that might be in that initial 10% or whatever of people that have never heard of any of these things, microcontrollers or microprocessors or whatever, like what would you suggest, you know, would be our first step? You know, like where do I have to go? Where can I get one of these? Like, do I have to install something on my computer? Like, you know, what do I need to do? If I just wanted to say, you know, I've programmed some stuff on my computer before and I've made some, you know, numbers change on the screen, but I've never actually interfaced with the real world. Like what do you think would be like the lowest barrier to entry thing I could do like tomorrow?
Yeah, that's a fantastic question. I would say get your hands on either an Arduino or a Raspberry Pi. Those are available from most decent electronics stores, very easy to get online. Let's say you wanted to build a system that, let's say a basic smart home technology. You wanted to build something that would flick a light switch using a motor whenever you pressed a button on it or something like that. The way I'd suggest to get started with something like that is to find a tutorial on getting started with a Raspberry Pi or a Arduino, look into doing receiving an input. So any basic tutorial will cover things like connecting a switch to a microcontroller, connecting a servo or a motor. I think there's a wealth of resources out there. The one I provided in the slide deck, I think, covers doing a case like that. But yeah, I think broadly, I'd say, yeah, a quick Google search of what you want to achieve will often lead to a really good starting point. There's a lot of resources on websites like instructables.com, which I'd highly recommend having a look at sometime. If you can think of a project idea, someone's probably posted about it there. Instructables has like it's almost like a giant database of different projects. So they'll usually provide instructions on how to do it, what components are required. They're definitely of mixed quality. Some are fantastic, some are not great, but it's a fantastic starting point. I hope that answers your question.
One good thing I'll add is just go on Tinkercad, pick an Arduino, and then look up some ideas on like how to create like a little LED circuit or something, and then you can basically expand from there because it lets you code on Tinkercad. So you can,
yeah, no, that's a fantastic idea. yeah, it's completely free online.
You don't have to buy it.
Tinkercad. Yeah, and you don't have to purchase anything. Don't have to buy an Arduino. You can just wire it all up virtually, which is fantastic.
Oh, is that right? That's awesome.
Yeah.
I didn't know that.
Try that out first.
That's a good question from Samuel Miller. When prototyping and or doing quick, dirty tests for various projects, do you use a fresh board / processor each time, or do you have a general purpose board as a test bed for many different things? Me personally, I will tend to use a different one for each. For software projects, less so. So if I'm developing just various software things, I'll often do that on the same device. But if anything as hardware, I do have a few Raspberry Pis and Arduinos around the house. And I'll usually start fresh for each one. But really, it's up to you. Yeah. I've actually got a question from Timothy here, who's looking to make a robot quadruped for his honours. They'll need a microcontroller for the robot and plan to have brushless motors that can be controlled through a CAN bus. The other option is servo motors. Yeah, that's a really good question. So for a quadruped, one of the key things I'd look at is how you want to actually handle positioning. So give me one moment. I'm just going to quickly double check terminology here. But in my experience, you want to look into integrated servos. So an example of these are the Dynamixel servos. These are fantastic. They're not particularly low cost is the only thing, but they all have their own independent motor controller in each of them, and they're servos, so you can actually do all the positioning. I've done a few attempts of doing something similar with just normal motors, DC motors, and one of the difficult things is getting that positional data, which you would likely need for a quadruped, depending on the exact design. With motors and brushless motors, which I haven't used quite as much, the brushless ones, but they will often optionally come with encoders, and encoders give you some sort of positional data, but it's essentially a Hall effect sensor, so a magnetic field detector. So when it spins, it increments a counter, essentially telling you roughly what position it is. I'm assuming brushless motors have similar things and similar encoders, but it's really difficult to work with if you want to actually get positions. The Dynamixels are fantastic for doing exactly that. So if you want to set a particular angle, you want to say, I want this leg at 40 degrees or whatever, that can be done. And there are cheaper versions of the same thing, but I would probably look into those for servo motors. Hope that gives you a bit of a jumping point. And certainly feel free to reach out if you want to discuss it further. Yeah, any other questions? Is there anything throughout the presentation that I sort of went over too quickly or didn't really explain well?
Just a delightfully good presentation, Connor. Thank you.
Thanks, Alex.
Agreed.
I do hope you learned something. Yeah, love talking about this sort of stuff. And there's always so much you can learn about it, and so many new applications for things. Yeah, and it's also a really good project, or there's a lot of really good projects you can do with absolutely zero experience. So for those of you who have done no real major projects or have only used them through university things, just take a look at some of the examples in the slide deck. I might even put that in the chat so you've all got access to it now, but you should also be able to find it on the Adept community Slack. But there's lots of just easy projects to get started with, and it's just genuinely a lot of fun to tinker with, to play. I remember one of the earliest things I did, it was sort of a robotics-oriented project. I got a Lego Mindstorms set for my 10th or 11th birthday or something like that, which, for those who don't know, it's like a Lego set with a programmable microcontroller on it, and you can actually move motors and servos and take input and all of that. And they're very popular for primary school and early high school robotics projects. And I remember I was watching the movie Real Steel, which was a half-decent action film from around the same time, and it features robots fighting. And I remember after going home from the movies, just playing around with that kit and building a robot that could box. And it wasn't very good. Don't worry, I didn't build the actual Real Steel robots, but it was easy enough to do because I had all the stuff there. I built a robot that could punch. It wasn't very great, to be honest, but it was a really cool example of just being able to build something with what I had there, and yeah, it was a lot of fun. Lockie's just asking how to get access to the Slack. That is a fantastic question. Tom or Alex, do you know if there's a link available? Or I might send it in the chat now and maybe post it to the event afterwards.
Worst case, just pop it on your personal drive and just make it accessible, and we'll make sure everybody here has Adept access. And it's probably a nice, very good reminder for everybody on the call. Let's take advantage of this fact, folks, that we've got a whole abundance of people with a variety of specialties. I mean, whether or not Connor likes to admit it to himself, he's been working with microprocessors and microcontrollers probably for 7 to 8 years. It's kind of a weird thing to look back on. And that is an unbelievable amount of experience, just regardless of anything you do. So there's going to be all sorts of people within Adept. Let's leverage them. Ask questions if you have any at all. When you feel that someone else has that area of expertise, and we're going to see that expertise coming out, as Sam has no doubt alluded to, in the form of these types of sessions. There's more to come. So yeah, get excited, folks. It'll be all available in the Slack. It'll all be there. So once everyone has access, make sure you're getting involved.
Thank you all for coming. It's fantastic, and I'm really glad I got to share all this with you. I do hope it was clear, but if you have any questions, as always, my email address is available and open.